Hi, so today I'm going to introduce you to Zenkai. It's a framework that I've been developing to extend the abilities of PyTorch. And yeah, so I'll give you a brief introduction of Zenkai and then I'll show you an example of how it's used. So Zenkai is a framework built on top of PyTorch to give you more control and more freedom of how you train learning machines. And yeah, so PyTorch is quite popular and it's extremely useful, but it's built on top of, or it's built with backpropagation in mind, which makes it a little bit limiting in terms of the types of machines that you build and also the types of training algorithms that you use. And so Zenkai aims to take PyTorch or to extend Torch so that you can more easily use approaches other than backpropagation. And yeah, so one thing I believe in is the importance of exploration. And so Zenkai's primary purpose is to encourage exploration and get researchers to try other methods besides just the back propagation. And yeah, so we need more tools to do this. And so Zenkai is one such tool that I hope can help with this. And so it aims to help give the researcher more control so that they can train neural networks or train learning machines with a wide variety of approaches and aren't limited by the by what backpropagation has to offer. Yeah, so I'll give a brief introduction of Zenkai. And so the core class in Zenkai is the learning machine class. And this learning machine class is essentially, well, you can think of it as a layer of a neural network or learning machine. And yeah, you can divide a learning machine into sub learning machine. And each learning machine can have autonomy over its learning. And one important thing is that, so typically the way you'd program it, machine is you'd have layer in choose or select the targets for the previous layer. It's not quite necessary to do it like that, but that's the typical approach that one would take with Zenkai. And yeah, it also offers many other tools. So, for example, like using population-based learning algorithms and stuff as well. So, yeah, I'll give you a brief example now, and then of what it looks like. So this is an example of a Zenkai learning machine, and to be simple, I used a typical gradient-based learning machine. And here you can see it's called linear. So it emulates what Torch's linear module would do, but it adds some more capabilities, as you'll see in a second. So you pass in the in features and the out features. Then after that, you have it defines the linear, it wraps the linear module in here, and then it defines an optimizer. And then the forward method, instead of a regular forward method as used in PyTorch, Zenkai uses the forward method called forward and in, and there are some reasons for that. But yeah, so it uses forward and in, and here you can see it calls the self.linear, and it passes in x.f, which f is the first value of this IO class here. So IO is a class that's used for the inputs and outputs into the machine. And then it defines an accumulate function. So this is extension of Torch. So the accumulate function is used to accumulate any changes to the machine or any changes to the machine's parameters. And since this is a gradient-based learner, it just does a typical approach. So it retrieves the output of the machine from this y value, assuming that the user has already called this forward and in. Here you can see that the output of the learning machine is retrieved, and the first value of the output is retrieved, and then assuming since we know that there's only one value for the output, then yeah, we just get the first value of the output, and then get the first value of the input, and then calculate the sum of squared errors and propagate backwards. And then in the step function, the optimizer is steps, and then the zero grad is called. And then lastly, in the step x function, the gradients are accumulated on this input x. And so this is the basic formulation for how a learning machine is defined. And so since you're given the accumulate function, which updates the changes to the parameters, and then the step function, which updates the parameters, and then the step x function, which decides on the targets for the previous layer, you can have more control over how this learning machine works. So for instance, let's say I don't want to use sum of squared errors. I want to try a different approach to getting updating the parameter or updating the changes to the parameters for this machine. Then I can use a different loss function. Now, sum of squared errors is actually what happens in backpropagation for each layer. So this is why it's used in this case. So next I'm going to show you an example of a machine built using the straight-through estimator. A straight-through estimator is used in order to get around the fact that certain types of activation functions, like the step function and the sine function, are hard, and so they don't actually have any gradients. But with a straight-through estimator, you still backpropagate through. And so one other thing with a straight estimator for the sine function is that you limit the range of outputs from the linear model that receive gradient updates to between -1 and 1. And so next I'm going to show you an example of a machine built with. So now I'm going to show you the straight-through estimator in action. So this is a Google Colab notebook that implements it using Zenkai's learning machines. And so first, let's run the installation. So you can see here that both Zenkai and Torch are installed. Okay, so now it's installed everything. And so then let's import Zenkai and Torch and also scikit-learn datasets. So scikit-learn datasets are used to construct the dataset that's used in this test. Okay, so here you can see that the sine learner is implemented and it inherits from learning machine, and it uses a straight-through estimation. It wraps Torch's inn.linear module, and also it has a loss function, which is the squared errors loss function. And you can see here that the reduction is set to none, and you'll see the reason for this in a moment. Then next, the forward and in function is defined, and here x.f is passed into linear, and then the value or the output of the linear model is stored in this variable pre-y here. And then lastly, the sine function is executed to get the output. And then in the accumulate function, so this is the most interesting function of this, and it shows you how Torch or how Zenkai can be used to implement wider variety of algorithms. Now, this straight-through estimator can actually be implemented by inheriting from Torch's autograd function without too much trouble. But I think it's also it's something simple, and that's why I chose it for this example. And so here you can see first the output of the linear model is retrieved. Then the difference between the output and the target is calculated, and then set to be the new target, or the difference between the output of the linear model and this difference here is used to calculate the new target. And then, like I mentioned earlier, there's a valid range of inputs that are used for backpropagating the gradient. And so if the output of the linear model is between -1 and 1, then the gradient passes through. And so next you can see the squared errors function is calculated between this pre-y and t, and then multiplied by the valid range. And then lastly, the error is reduced and multiplied by 0.5. Then the backward function is executed. And lastly, so this is the step x function is rather simple in this case. So all you do here is you accumulate the gradient on x. So next is the training loop. And the training loop is a pretty standard training loop, so I'm not going to go into too much depth about it. But you can see here that first that the data set is created and the optimizer is defined. Now, in this case, I'm defining the optimizer outside of the learning machine, but actually it could be defined within the learning machine. But the reason I'm doing it outside is because actually there's two layers in this case. One uses the sign learner, the other just uses a regular torch or inn.module. And then, yeah, so this is the standard training loop here, and the loss is calculated, and then you call the backward function on the loss, and then you use the step method on the optimizer. So let's execute this now. And then lastly, so let's define the sign learner. It's defined as a sequential model with the first layer is the sign learner, and then you have the regular inn.linear module, and lastly the sigmoid is called, and these are all passed into the train function to run the training algorithm. And yeah, as it runs, you'll see that the error gradually decreases, so it actually shows that this is learning and the straight through estimator is working. But just to confirm that the straight through estimator is working, after this gets done training, I'm going to change the requires grad for sign learner to true. To false. Okay, so now it's done training, and we can look. It's run for 1,000 epochs, so we can look and see what the error was at the end, and you can see it's 0.22, which is a large improvement over the initial value, which was, I'm not sure exactly what it was, but after 9 epochs, it was 0.64. Now, let's, just to show you that this sign learner is actually helping learn, let's change the requires grad property to false, and then let's run this again, and you will see that actually the machine doesn't really update anymore. To show you that it does actually not learn very much once requires grad is set to false. And yeah, I think it's run for enough, and you can see that it's not really improving after 230 epochs. Yeah, so that's it for today. So I've given a brief example of Zenkai. I've introduced you to Zenkai and told you about the reasons for using it. And yeah, so next time I will go into a more interesting example of things that you can do with Zenkai. Anyway, thank you very much.